is we can start in our state space, which I've written out here, and we can transform it into the Laplace transform the same way that we would any system. So we're going to use the Laplace transformation to find the transfer function. So again, let's remember the transfer function is going to be the output, which in this case is y.
So if you have
The index
space,
is u.
how can you
It's not r.
transform into transfer function?
So let's take the Laplace of this and see what happens. Okay, so one derivative, so we get s, x of s.
So for state space, we have parameter A, B, C, D. For transfer function, we have parameter G, B, S.
Y, do it here.
So how can we convert A, B, C, D to G, B, S?
X of s plus d.
So first we take Laplace.
And in our
Here,
transfer function,
here,
we only want to
here,
convert input and
here.
output. So we really want to get rid of this x. So we can move these things around.
So
put
take
these
the Laplace
equations together
from equation
and
1
get rid of our
and the
x.
equation
So
2.
let's
So you
rewrite
can
our
take
first
your
equation here.
assignment back. And then you can get the Laplace transform.
So we want to move all the x's to one side, so we'll do x of s.
So from this equation,
And then this will be
then develop
s.
XS.
We're minusing a. Okay, oops. That's an
So
a.
we combine first
And then
and
over here we
this step.
have b, u. Okay, and we want to divide by this value, but we're working in matrices. And actually, when we do this, because we're working in
So
matrices.
S is a scalar, A is matrix. So you have to multiply
Move it
by
over, we get this expression.
identical
And
matrix.
when we, this is a matrix, because we
Otherwise, you
have to have it in a
cannot
matrix form. So
do
we need to
mathematical
do
process.
So we need to take the inverse and apply it to both sides. So
Then you can take the
end up
inputs.
with the inverse of this, so is minus a inverse, maybe 1, then times the b and the u.
So this is a relationship between
Okay.
you and the state.
Well, now we can use
X.
that and put it into this equation. So this right here, replace it there so that we can get rid of our x.
So
And
we
then
can found
y
the
s
state
here
state
equals c
XS
times
is related
y,
to
this
US.
part. So the inverse of is
Then you can
minus
find
a
the relationship between YS
And one
and
inverse.
S.
times b u of s.
This is
That was this
input.
whole quantity.
This is output.
Oops, I will close it. Oh, no. It's not extra bracket there, sorry. This is the bracket here,
So
and then this, we
this is
substitute
input.
x in here. Now
This
we
is
have
output.
d and u, us. Okay, well, we have, okay, we'll separate out u here,
Okay.
and we'll actually move it
So we
straight down
have
over
two
here.
input. We can combine
We'll get
these two items.
y
So
of
Y
s
is output.
over u
U
of
is
s.
input.
So we're going to
This
take
is
it out
transfer
of one of these
function.
and then move it over. So now what's left over here is c of is minus a inverse b, and check out the u, and plus d. So these are all our
So this
basic
is
values,
transfer function.
and we can use that to find the transfer function. So this would be,
This is transfer function.
Of S.
GPS.
and we can use, then this is our base equation. So this is a really important equation for going between the two.
So this is
You don't have to
equal
derive it every time, if you just remember this equation, and you have your system
One,
is
the transfer
plug all these
function
values in,
from state
calculate,
space
and you can get
A,
the
B,
transfer function.
C,
So
D.
we'll do an example with that in a second. So I've rewritten the equation we just
GP
derived to go
is
from the state
equal
space
to C
to the transfer function right here.
SI minus
And
A
we're going to
equals
recall
B
our
plus D.
dollar on a spring system.
So if we have A
And
matrix, B matrix,
modeled it
C
in the
matrix,
state space, so I'm
D
writing
matrix,
out
we
the
can
components
calculate
here.
transfer
So we are
function
going to
GPS.
evaluate this transfer function. Okay, so let's start by just writing everything out. So GP of S is going to be equal to C,
C was 1.
1, 0. And then
X1
the identity
is
is
I
S
minus A
minus A.
equals.
And we're going to take the inverse of that, so
So
we'll
S
start
I minus
with writing
A
this out. So it would
equals.
be S minus 0.
This is
And
S.
here, the lower
This
bottom
is
right would
S.
be S minus this value, so plus B
So
over M.
minus A
And then here we just get negative, so we
Minus
get negative
A.
1 here. And then a
minus
positive
0
K over M here.
and then
Okay?
minus
And then we
minus
still take
A.
the inverse of this,
So
but
this
we
is
will,
S I minus A equals.
and then B
B.
will
So
be
you can copy B.
0, 1 over M here. And then plus
this
D.
is C
Our D is
S I
0.
minus equals multiplied by
That
B
is our
plus B.
expression written out. Now, the inverse is probably the least fun part of this. So let's just remember
So you
how
have
to do
to
an
compare
inverse real quick.
inverse.
So if you recall, make this smaller. Okay,
How can we
we
calculate
have a
inverse?
matrix A, B, C, and D.
So this is
And we're gonna call
one
it,
matrix.
just not to confuse it, we're gonna call it E for now. Just so that
So you have E
Just think
matrix.
so.
You want to find the
E,
inverse
this
of
is E,
E.
then the inverse
You
is
can get back your
is going to
assignment.
be 1 over the
You can get
determinant
back your
of
assignment
E,
and the
the
reference.
determinant of this matrix, times, and you have to flip these two, so it's D and A here, and then take the negatives of these, so negative C.
And your assignment also.
Okay, so, not the most fun, but let's take the determinant of E, so the determinant of this matrix here. So, we'll keep everything in its form, so here you still have 0, 1. Now we're taking the determinant of this, so
So
1 over that.
this is inverse.
And so
You
it'll
can
be
use
S,
this formula.
S plus B
So
over M.
determine E,
This times this, minus this times this, so it would be a plus
determine
K
E.
over M. So there's our 1 over the determinant. Now we need to just flip
We
these
have
things
to
around, so
Switch A
swap
and
these two,
E.
so we get S plus B over M here, and then S in the bottom right, and then take the negatives of these, so negative K over M, and then positive 1. Okay, so there's our
So this
inverse.
is
So let's
inverse.
multiply that by 1 over, and then the 1 over M here. Sorry, 0, 1 over M. And then we don't have to
Plus
add
zero.
0. So here's, now we're here. Now we need to evaluate this, so let's start from the right. So let's look at multiplying these two matrices together. Remember, this is a scalar, so we can leave it kind of in the middle here. And we're going to multiply this
This
out.
one and this one.
Rewrite everything.
So
And
copy
we're
here.
gonna actually shorten this a
Copy
little bit.
here.
1 over S squared plus B over M, S plus K over M.
So this copy.
Alright, and
And
so
now
if
we
we
multiply
multiply this
this
out, we'll
one
get
with this
0 plus 1 over M in the first spot, 1 over
This
M.
one to this one.
And then 0 plus
Second one.
S over M.
This one.
Okay. Okay, so we're getting closer. And this again is our scalar, so we can actually move it out to the front and we can do the multiplication of these two matrices. So 1 plus M times 0 plus, we'll write it up. 1 over S squared plus B
This
over
one
M,
and this one.
S plus K over M. This is our scalar out front, so now let's multiply these two matrices and we'll get
So we have
1
the
over
first
M
item.
plus 0.
Zero.
Okay, so now we have a scalar here, we can multiply this all out. Why don't we actually move the M to the bottom? And we will get GP of S.
So this
the
is
transfer
transfer
function is equal to 1 over, so M times S squared plus
Plus
M times B over M, so
second
B
item.
S. Multiply the M, so plus K.
So this is
And
the
this-
transfer function.
Should be equal to our transfer function. If we go back and check the original transfer function that we did, we'll see that they are the same. So this was successful in our transformation. Probably the most unfun part about doing this transformation is doing this inverse. if you get a very large A matrix, it's best to use MATLAB rather than trying to do it by hand. But with this one, 2x2 is usually not too bad. So we're able to take the state space. If you don't like state space for some reason and you want the transfer function, then you can transform it using this equation.
So this video show how can we convert the state space into transfer function. So if you have a system, how can you represent the system? You can say x dot equal to ax plus b, y equal to cx plus d. Then you have transfer function. So my question is, if you know state space, can you get GPS? Yes or no? Can you compute GPS? If you know ABC, D, can you compute GPS? Yes. How many solutions? One solution, two solutions, or infinity solution? If you know ABCD, you want to compute GPS, how many solutions can you get? If I give you assignment, give you A, B, C, D, and we have 20 students, how many solutions will be the transfer function? Infinity? Or 2? How many? Only one, right? Every student should get the same transfer function. So only one. On the other hand, if you know GPS, how many ABCD can you get? If I give you a transfer function and as you tell me ABCD, how many solutions? One, or two, or infinity? If you think one, please raise your hand. If you think two, please raise your hand. If you think infinity, please raise your hand. So which solution? If I give you A, B, C, D, and ask you to compute transfer function, so this is state space. This is transfer function. If I give you A, B, C, D, and ask you to compute transfer function, there is only one transfer function. Now I give you transfer function and ask you to find A, B, C, D. How many A, B, C, D can you obtain? One, or two, or infinity? Anyone has any suggestion? TPM, how many?
Infinity.
Infinity. So what does this mean? If I say we have assignment, we have midterm exam, we have final exam, then I give you each student get 90 for assignment and I get 80 for midterm, 80 for final exam. Can you compute his final grade? Can you compute his final grade? Yes. How many score can you get? Only one. Everybody has the same result, right? So you can compute. So this is 27, this is 28, this is 28. So finally, this is his score. But now I give you the score. his score is 83. Can you tell me what is his assignment? What is his midterm exam? What is his final exam? So how many solutions? How many solutions? Infinity. We don't know. So do you think which one is better? State space is better or transfer function is better? Which one is better? If I know state space, then I can compute transfer function and the unique solution. But if you give me transfer function, can I return to state space? No. So which one is better? State space representation provide more information, not only input output, but also state variable. So in general, state space is better than transfer function. Transfer function is just like a black box with input, with output, and then this is transfer function. But the state space tell you what is the state inside, what is the state, what is input, what is output. So in general, state space provide more information. So we discussed about the first item. How can we convert state space into transfer function? So the answer is so this is the solution, right? This is the solution. So you can compute unique transfer function. So now we will watch another video about analysis of converter transfer function. We directly use the transfer function. So now this lecture try to directly discuss the transfer function.
We'll continue our discussion of frequency response and
Transfer function of the buck boost converter. We just mentioned last class, right?
So in this
So this is the result.
we work through construction of the transfer functions of the buck-boost converter that we modeled in chapter
So
7.
the model is like
So
this.
again, here is that equivalent circuit model that we
So
found.
this is
And
black
what I'm
box
going to do
right
now
here.
is work out the asymptotes of the magnitude phase of the control to output and line to output transfer functions.
So this is transfer function.
So we've discussed this before as well.
So output ripple.
The output voltage V hat
This is
as the
output
output of
ripple.
our circuit. And we have the control input
We
V hat
have
and the power input VG hat.
The variation of the duty cycle and the variation of the input voltage.
As a linear combination of terms that arise from each of the
So they will influence the output
And we
ripple.
already talked then about how to find those transfer
So
functions.
how can we find the transfer function?
The transfer function GVD is found by first setting the
So
other
first we want to
VG at
find
0,
This transfer function, it is V
and
hat
then find the ratio
divided by
of V
D.
hat over D hat.
So at that
And
moment,
then
VGS
find
is
the
0. We only consider this item.
Likewise, to find
And the
line
second
transfer
item,
function
we
GVD
neglect this one, D
set
equal to
V hat
0.
0,
And we can calculate the second item.
G hat. So let's work through the solution of each of those and then construct the transfer functions.
So
So first, to
how can
find
we construct the
GVDS.
transfer function? So CVG from input ripple, output ripple. So at that
So
time,
we'll set D
D
hat
hat
0.
is equal to
What
0.
that does to the D hat voltage source here is to turn it into a short circuit.
Because D is 0, it's become short circuit.
And to the two current sources that depend on D hat,
D
we
is
set D
0.
hat 0, they become open circuits.
So it's become open. D is
So then the
0,
circuit
so
reduces
become
down to
open.
this one.
So it is like this.
Okay, next we can push all of the elements to the right through the transformers So if we push the inductor through this transformer,
So it
we
becomes
have to divide by d prime squared.
now we have
which is
transformer, so we can
here. And
refer
when we push the VG
this
hat
one
source to
into
both
the second side.
transformers, we will, let's see, multiply by d, divide by d prime, and then we have to
So we
reverse the
refer
direction because
the parameter into the second
So
side.
VG hat times minus d over d prime for that source.
So the source becomes this
So
one.
now we have this
So this
circuit.
is the equivalent circuit.
And finally, we can solve this using the voltage divider formula.
And
So
we can calculate
View
The
this
output
impedance
mark
as the
divided by
parallel
input.
combination R and
So we
parallel
can calculate
combination.
V hat,
And we
VG
have
hat.
this impedance is SL over d prime squared. Then using the voltage divider formula, we can write the transfer function this
So
way.
it is like this.
So we have the coefficient minus d over d prime out in front, and then multiplied by the voltage divider formula. Okay, at this point, I would say R in parallel with 1 over SC
I and
comes
C
up
parallel.
a lot, and it's worth working it out and writing it down and memorizing what it is. R in parallel with 1 over SC is R times 1 over SC over R plus 1 over SC. If you multiply top and bottom by SC, you get R over 1 plus SRC.
So this one is equal to this one.
So we can plug that in.
So we have two
Here.
series. This one
And next,
this one.
we can multiply top and bottom by 1 over SRC to turn this into a rational fraction. So if you do that, you get this expression.
So we can see the relationship.
Now, what I would say at this point is we
Transfer
still
function.
aren't quite done because we need to write the poles and zeros in normalized form where the coefficient of s to the 0 power is 1. So we should divide the top and bottom by
So
r
we can divide both sides by R.
to get that to happen. If we do that, then we'll get 1 in the numerator, and this coefficient of s to the 0 power in the denominator will become 1 as well. So that's shown on the next
So we
slide
can
right here.
simplify
Finally,
here.
here's the answer to
So this is second order, low pass, second order.
Okay, we recognize this form now as having a gain out in
So
front.
this is
or
the gain.
what we call GG0.
GG
And then it has a
is the
quadratic
gain. And
denominator.
this is
So
the
we
second
write the
order.
denominator in the standard quadratic form, which we discussed last week, like this. Okay, by equating like terms,
So this is the transfer
we
function,
have
which is a second order,
we can get
low pass
equations for
filter.
salient features. So GG0 is apparently equal to minus d over d prime for this converter. The coefficient of s squared in our normalized form is 1 over omega naught squared, and that should be the same then as this coefficient LC over d prime squared. So you can solve for omega naught.
So you can calculate omega 0
Prime over mu LC.
from the relationship.
And then finally, the
You
coefficient
can
of
also
s
calculate
first
the
power
Q,
would be 1 over q.
the
omega
quality
naught in our standard
coefficient.
form. That should be equal to L over d prime squared
This
r.
one equal to this one.
So you can plug this expression from
And then
omega
you
naught
use
in here
omega
and
naught
solve for omega
here,
q.
then you can
and
calculate
get an
Q.
equation for q.
So you can obtain Q.
Then here is the
omega
result.
0.
Here's a summary of our salient feature expressions. So we have GG0, omega naught, and Q written as nice simple formulas. Okay, now let's work out the control to output transfer
So this is
function.
the transfer function of the buck boost converter.
So this is V hat over D hat, again with VG hat.
So now we want to calculate.
So if we let VG hat
V
be zero,
hat,
it
Q
shorts
hat.
out this VG hat source.
And the VG head becomes 0. Short circuit.
Shorting the source shorts out the current source on the input side as well, which and shorts the primary of the transformer.
So short
So effectively
transformer.
all the secondary
So
is
short.
like a short circuit.
Second side transformer.
So then the circuit reduces down to this.
So we can reduce to
We
this.
can continue and push this voltage source through the
Then we
transformer.
can
We'll have to
take
divide
this
by
voltage,
the
refer to
current
second
ratio
side.
and reverse the flaring because the dots are
Then we
reversed.
have this
That
one.
gives us this source. We can also push the inductor through the
We can
transformer.
refer the
divide by
inductance
the
into
current
second
flaring
side,
case
become this one.
And so the circuit now reduces to this.
So then we can combine the whole
Well, we
circuit.
still have two D hat sources, so we have quite a bit of work still to solve for the output voltage. Here, we can view V hat as actually being
So this is
superposition
output,
of terms coming
and
from
this
these
is
sources.
input
Even though the
D
two
hat,
sources are both D
and
hat
output
sources.
V hat.
We can still
So
write
which
V
means
hat
the relationship
equal to one
between
transfer
output
function
ripple
times
and
the
the
first source
duty cycle
plus the
ripple.
second transfer function times the second source. So then here is that.
So we can use
Here's the
superposition
the first
to
transfer
combine
function times the
two
voltage source
items.
with the current source that would have been here set to 0. And here's the second case where we set the voltage source to 0, and then we get the current source driving these impedances. So for the first case, we can again use the voltage divider formula. The output voltage is this
So
coefficient
the capacitor parallel with R
multiplied by the divider ratio.
and then series with
And the divider
inductance.
ratio is in the GVG transfer function. In the second case, we have the current source driving a parallel combination of impedances. So we can write that the transfer function here is the coefficient I multiplied by the parallel combination of all three elements. By use of superposition,
So finally, we
add
can
these two
obtain
together,
the relationship
transfer function GVD.
between the output ripple
There it is.
and the input duty cycle ripple.
Still pretty big, long expression, and it will take quite a bit of algebra and work to simplify it and write it in the standard form. Frankly, I think that it's easier actually to manipulate the model into canonical form and then solve it that way. But this is still a valid way to do it, and if you are able to do the algebra, this is maybe the most straightforward way. So what I will say, I'm not going to do all of this algebra here, but if you simplify this expression, you can get it down to this one, in which we have a DC gain.
So this
We
is
have a right
DC
hand
gain,
zero in the numerator.
This
We have a
is
quadratic
second order,
that is
and this is
equal to
first order.
GVG.
So finally,
this
we can get the transfer function
written in this
like
standard
this.
form,
So this is
where the
output ripple
coefficient
to
G
duty
zero
cycle
is this
ripple.
term here. The right half plane zero frequency omega z would be 1 over this quantity. And the denominator Q and omega naught are the same.
So this is second order.
So then here is a summary of the
So this is
equations
the
for the
summary.
setting features in
So
this
we
case.
have get, we
One other
have
thing I would note
omega
is
zero.
that to simplify the
We have
expression for
Q.
omega z zero from this form into this form, we use the DC relationships that come from solving the DC model. Okay, so we
One
have a
example.
nice analytical result where we
We
have
have
for
the
setting
parameter
features. At
resistance
this point,
duty,
we like to
VG,
plug in the
LC.
values and construct the
and
bar.
we want to use the numeric to show the real value.
These values for the element values and duty cycle. So if you plug those into our expressions, you get these.
So we can
quantities.
calculate
So the
the DC
DC gain of AVG is 3.5 dB.
And the GT zero.
5.
and
DC gain of
frequency.
the control 12
And the
transfer
Q.
function is
frequency.
187.5 volts. It has dimensions of volts because the duty cycle is dimensionless while the output is voltage. Expressed as dB, this corresponds to 45.5
So this is
volts.
DC gain.
Then we have our quadratic poles at 400 hertz with a Q of 4, which is 12 dB.
This is the
And
quality
right after
factor.
zero turns out to be at 2.65 kilohertz.
So you
And
can
then here's the
obtain
plot.
40 backwards.
So this is the control to output transfer function. We have our DC gain of 45.
So this is DC gain.
We have two poles
This is
at
Q.
100 hertz. After 400 hertz, the function starts to decrease with
So you can see
per decades.
the bandwidth.
And we have a Q of 4.
Calculate the bandwidth.
Have not. So there's a resonance here. And
So this is rather
the
than
value of the function
the whole peak
at
and
400
the
hertz would
40
be
down.
12 dB plus 45.5 dB.
So it is a low pass. A low pass. Okay. So this is 40 diagrams. So we call this is 40 block.
At the right half plane, zero frequency of 2.6 kilohertz. The zero adds plus 20 dB per decade slope.
So this
the
is
positive
20 dB
slope
per
of
decade.
The entire transfer
Decade.
function then will be minus 40 plus 20, which gives us minus 20 dB per decade slope beyond 2.6 kilohertz. Here are the phase asymptotes. We
This
started
is
at
the
0
phase.
degrees. I actually haven't included the minus sign in the transfer
This
function
is
here.
gate.
Although
This is
since we have
phase.
a negative output voltage, there is actually a minus sign, which would be another 180 degrees of phase, and that's not included in this plot. If we work out the phase asymptotes, the right half plane 0 will have a break frequency of 1/10 of 2.6 kilohertz, which is 260 hertz, and it's shown right there. That's the first break frequency that we get to. And beyond this 260 hertz, the right half plane 0 will contribute a minus 45 dB per decade slope, all the way up to 10 times 2.6 kilohertz, which would be 26 kilohertz. So we have minus 45 degrees per decade there for that range. And then, in addition, the complex zeros contribute a slope here that's very large. The slope, recall the formula, is minus 182 degrees per decade. The Q is 4, so that would be 4 times 180 negative degrees per decade. So we get a very large slope over this range of
This
frequencies.
slope
It's
is
basically
huge.
from 10 to the minus 1 over 2Q times 400 hertz, it works out to be 300, up to 533 hertz, which is 10 to the plus 1 over 2Q times 400 hertz. So here are the composite phase asymptotes, and at high frequency, we finally end up about 26 kilohertz.
So this is
And the
high
composite
frequency
phase
minus
asymptote of minus
170.
sorry,
degree.
minus 170 degrees. Here are the asymptotes for the line to alpha transfer function of the buck-boost converter, and again, they don't include the
So
minus
this
sign.
is the voltage gate from output
Very
report
large.
to input report.
This transfer function looks similar
So
to
you can
the
see
control to
this
alpha
line.
transfer function.
So this is
except
rather
we
than-
have different DC gain, 3.5
So this
ohms
is
in this
DC
case.
gate.
And it doesn't have the right half plane 0. So the high frequency asymptote is minus 180 degrees rather than minus 270. But otherwise it's similar. Okay, so we constructed the control to output and line to output transfer function of the buck-boost converter. I went through really the direct algebraic solution of the model and developed the expressions for the salient features, which we then used to construct the asymptotes.
Okay, so why do we need to do this mathematical model? Because we have to determine the gain margin and the phase margin, and then we can design the controller for closed loop. So we need to develop the mathematical model. So there are two ways to develop the mathematical model. One way is using state space representation. X dot equal to AX plus BU, Y equals to CX plus DU. And another is transfer function, the output divided by input, so small singular. So this is the main idea. So we will continue our lecture. So in last class, we discussed about state space averaging. So what is state space averaging? Because we have switching. One is Q on, D off. Another is Q off, D on. So we have different mathematical model. But to design controller, we only have one controller. So we have to combine the two models into one. How can we combine two models into one? We can use state space averaging. So what is state space averaging? We have A1 for Q of D of, A2 for Q of D of. Then A1 duty cycle is D. A2 diameter of duty cycle is 1 minus D. So we can combine A1 and A2 become A, right? So how can we combine A1 and A2 become A? If your duty is larger, which means you are more important, right? So we multiply by D for A1. And this is diagonal off, so we multiply by 1 minus D multiplied by A2. And then we multiply by sampling time. So A equals dA1 plus 1 minus dA2. It is equivalent, right? So we call this is a state space averaging. So how can we use state space averaging? There is one condition. You should be switching very quick. If your switching is too slow, then you cannot combine these two together. So it is only good for high frequency switching. So this is the basic idea. So then what can we do? We can combine A1 and A2, B1 and B2. So finally we get A is here. And then X dot equal to AX plus BU, right? So what is A? A combined from A1 and A2. So dA1 plus 1 minus dA2 become A. How can we combine B? dB1 plus 1 minus dB2 become B. So you can see this is A, this is B. And C is always 1, 0, so no change. So I give you assignment, ask you to calculate the steady state condition. This is dynamic equation. So what is steady state? Steady state means what? Stable, right? So you have transit, finally, steady state. Steady state means what? No change, right? No change. So what does this mean? This means no change. So your deviation should be equal to what? 0. So I'm moving. This is dynamic. Now I'm here. This is steady state. I don't move again. So X dot equal should be equal to what? 0. So then this is equal to 0. Right? This is 0. Then if this is 0, we can say AX plus BU equal to 0. So how about X? AX equal to, we can move to here, minus BU. Then how about X? X equal to A inverse minus BU. So you can see here, right? So this is steady state, right? So now we can use A matrix. A matrix is here. We can put A inverse, compute A inverse. We can compute B. Then we can find the relationship between X and U. So what is the relationship? Okay. Let's check here. So this is A inverse. A is here. We know A inverse is here, right? This is B is here. This is U. So finally we can find X equal to what? DVSR and DVS. So what does this mean? What is X1? Did you remember what is X1? X1 is equal to IL. What is X2? X2 is VC, right? So in steady state, what is your output? The output is here. So you can see this is your output. So your output is VC. It is duty multiplied by Vs. So this is buck converter. So what is the output voltage of buck converter? Did you remember? You have input Vs, you have switch, you have diode, you have inductor, you have capacitor, you have output voltage. So what is the output voltage? Duty cycle multiplied by what? Vs, right? So did you get the same result? Yes. In steady state, the output is equal to duty cycle multiplied by input voltage. This is what you have learned for DC buck converter, right? How about the inductor current? So now I ask you, what is the inductor current? Inductor current includes two parts. One is IC, one is IR, right? So inductor current, IC and IR. What is the average of IC? Anybody has any idea? What is the average of IC? If IC is 1 ampere, then the voltage increases to infinity. If IC is minus 1 ampere, then the voltage decreases to 0. So what is the average of IC? What? 0. So the average here is 0. Then how about IL? IL is IR. What is IR? IR is VC divided by R. So you can see this is VC divided by R. VC is duty multiplied by Vs, right? So do you have the same result as before? Yes. You can see if I set x dot equal to 0, then I can get DC result. So you can prove this math is correct. So for AC response, what is AC response? X per dot equal to AX per plus BU per plus, this is A1 minus A2 X plus B1 minus B2 Vs multiplied by the duty cycle variation. So we can write down here. So what is the Laplace transform? We can take this Laplace transform Sx minus initial value 0 x 0. This is Ax Bu B1 VSD. Then we can obtain this one. So we can find the x equal to this. So what is Si minus A inverse here? So we can put here into Xs. Then we can solve Xs here. So Xs is related to control input. So what is the relationship? C Si minus AB. So here. And finally, we found here. This is input ripple. This is a state ripple. The first one is inductor current variation. So the relationship is here. The second one is output voltage ripple. The relationship is here, right? So we can calculate IL per and VC per, which is related to the input ripple. Then we can draw the body diagram. So as we watched the video before. So we can make a simple summary. In this section, what did we discuss? We discussed the different type of DC-DC converter, including flyback, forward, full bridge, and choke. And for this one, it is non-isolation. We have no transformer between input and output. As a result, the node is easy to be damaged if the converter is fault. So we propose isolation converter. Then we use transformer. Then we discuss about the modeling of DC-DC converter. How many ways can you develop the modeling? 2 ways. One is using what? State space. Another is using what? We call AC small signal, right? 2 ways. And then we will discuss about the control of the DC-DC converter. So I think this is the chapter, and we will have 20 minutes break.